the law of our process evolves in time. And so this is based on a series of works with Massimiliano Gubinelli over the last years. And towards the very end, I will present a new, or I will somehow shadow maybe, the shadow of a new idea by Lukas Gräfner, who is a master's student here in Berlin, who gave some new perspectives on this, who had some new ideas coming from functional analysis, which somehow simplify some of our constructions and allow us to go a bit further. Okay, so I will start quite basic today, just with the motivation. So I already said a bit what we will do. So we want to do this martingale problem for locally subcritical, and this is the new input, in some cases even for some critical SPDEs. But so this will be for very specific equations, and I will later mention what kind of equations we can treat with this approach. Why do I like this very much? So I enjoy working exactly in this, somehow looking at these equations from this perspective, because one nice aspect is that you get to combine tools from lots of different fields. So some stochastic processes, hydrodynamic limits, we need Gaussian analysis, a bit of infinite dimensional analysis, but we also bring in ideas from this regularity rough path way of thinking about the problem. And now also more and more functional analysis. And on the other hand, so we somehow serve ourselves from many different areas. And on the other hand, we don't need to dive in too deeply in all of that. So I think compared to the other lectures we will see this week, I'm not going so deeply into the analysis and so deeply into the mathematics. So by picking your tools from everywhere a little bit, you manage to stay relatively lightweight. I will comment on that a bit more as we go along. But so one aspect, for example, is that subcritical equations in this approach don't really distinguish how far away you're from criticality. As soon as you're subcritical, it doesn't make any difference. So if you have a parameter which approaches a critical value, then as long as you're away from that critical value, the analysis has the same level of difficulty, while in this regularity paracontrol distribution approach, we see more and more complicated expansions the closer we get to criticality. And yeah, why is this useful? I mean, we have a solution theory for these kind of equations. Why is it useful now to come up with a different solution theory? Well, one aspect where this comes in is scaling limits. So there it is natural to talk about martingale problems. So that's one of the main tools for proving scaling limits. It is quite easy in this formulation to prove ergodicity. It comes down to 3-4 line proofs or so. You can derive functional inequalities. So martingale problem means we construct an infinitesimal generator, and then we can prove functional inequalities for this generator, spectral gap inequalities, for example. Controlling moments comes essentially for free, which can also be a pain in the pathways approach. We can study fluctuations of our process. And this is the new aspect maybe. We can also treat some critical equations, although we can just prove well-posedness. And for example, it's not so clear if the model is Gaussian or not, but in any case, it is well-posed. Okay. So by the way, I'm starting now from this bird's eye view, and my aim is actually to be inclusive with these lectures. So I suspect that I will bore more people than I will somehow go too slow rather than go too fast. So I will start from quite basic aspects soon. But just in the beginning, I want to show where we're going. And then after that, if there are some terms which don't make sense to you, for example, critical, subcritical, and all that, which by the way means something different than in Hugo's talk. So if it doesn't mean anything, it doesn't matter. I will start more basically once we get through this introduction. So what kind of equations can we do? So the main equation we will talk about here is the conservative stochastic Burgers equation. So this is an equation in one time, one space dimension. I will always argue on the torus. It's not so important. In principle, you could also put R here, but it simplifies a few arguments to be on a compact space without boundaries on the torus. And then we have this heat equation here. Here we have the Burgers nonlinearity. And here we have the derivative of the space-time white noise. So this is why it's the conservative stochastic Burgers equation. So conservative means it's preserving the average over the torus. So the integral over the torus, delta t of this dx is equal to 0, because you see on the right-hand side, everything comes with a derivative. And if you integrate the derivative on the torus, then by periodic boundary conditions, this integral is 0. Another equation we can treat, which I will speak about at the very end, is the fractional multi-component. Well, I will not speak about multi-component, but we can do fractional multi-component Burgers equations. So the domain is the same, the states, the input is the same, but now the output is a vector. So we map to RD, or rather to d-dimensional distributions. And we have a fractional parameter here and here. So we have some fractional Laplacian here, and then exactly half this theta here. And this is to somehow get closer to this critical parameter. So the higher theta is, the easier the equation becomes. So for theta equals 1, it's basically the previous equation. I will comment on the multi-component part in a second. But if theta gets smaller, it gets more singular. And at 3/4, the equation becomes critical. Again, I will explain later what it means. And so we can do theta bigger than 3/4, but also theta equals to 3/4 if the prefactor in front of the quadratic nonlinearity is less than some given threshold value. And this is based on this new idea by Lukas Gräfner that we can do this. And so what about this RD and this kind of thing here? Well, this is now vector valued. And yeah, so this means we have to replace the square here by a bilinear form. And the bilinear form can depend on I. Yeah, so this here is a symmetric matrix for each I. And then you take this bilinear form, then you take the derivative. So basically it's a vector value generalization of that. One thing which is important here, this thing needs to be fully symmetric. So this, if I fix I, it's a matrix of 2 inputs. So we have basically three arguments, and it has to be symmetric under any permutation of these arguments. So this is this trilinear condition of Funaki that Funaki came up with. If you put a general gamma here, then we don't know anything anymore with this approach. Another equation is a sort of Navier-Stokes equation. So this is work by Massimiliano Gubinelli together with Mattia Turra, where they, it's a bit, I'm oversimplifying it a bit. It's not quite correct what I write here, but basically, yeah, you have this Navier-Stokes nonlinearity with this divergence-free condition here. And then you have a Laplacian or this is an Euler nonlinearity. And then you have this fractional Laplacian with a theta bigger than 1, and here a noise which is somehow compatible with it. And okay, so just to go through the list further, you can do some modified surface quasi-geostrophic equations. Those have been done by Luo and Zhu. And modified means, okay, there's a certain parameter, and if you put this parameter equal to 2, then you get the Euler equation. If you put this parameter equal to 1, then you get the surface quasi-geostrophic equation. And in this work, the parameter is between 1, strictly between 1 and 2. Here we do the parameter equal to 1. So this is in the master thesis by Lukas. And also there's been some work by Nathan Tots. And the general requirement under which this approach works is we need a quadratic nonlinearity, a Gaussian invariant measure, let's say Gaussian invariant measure, and, well, subcriticality. Okay, and here we will only treat this equation, Burgers equation, and for most of the talk, and actually there's a minus missing here, for most of the talk, the theta will be equal to 1. And then, I mean, if you put theta equal to 1 here, then this is a derivative of order 1, right? And then somehow statistically, so from the law, it's the same as taking the usual derivative. So we'll take this derivative. Okay. And now, so this was somehow trying to explain where we're going. And now I take a step back and try to explain why we're doing it, and then somehow slowly develop the theory as we go along. So here I just want to explain why these singular, what are singular SPDs and how do they arise? And basically I want to justify why do we see white noise in SPDs? Why is space-time white noise? So effectively we will see problems in our equations because we have space-time white noise, and I want to explain why we would see space-time wide noise in SPDEs. Why can't we take some more regular noise for which all our problems would go away? And the idea is that you see SPDEs typically on a sort of mesoscopic scale. And so here's a very coarse caricature. So these are these interface models. It's not so important that this interface could be any kind of model, but interface is easy to explain. So for example, here we have these snow crystals that are piling up. And if we now look at this on long time scales and from far away, then effectively we will just see this line moving up. This is what I depicted here. And here we have some bacteria and some nutrition. So on long time scales, we would just see these circles grow outwards and outwards from some of our core scale. And this is some simulated model. This would also just go up linearly. So this would somehow be the macroscopic scale. If you would go to the microscopic scale, you would see maybe something like single molecules. So basically something extremely irregular where either there is something or there's nothing. So somehow, yeah. So on the microscopic scale, things would look extremely irregular. On the macroscopic scale, things would look smooth. For example, just this line here moving upwards. And now to see an SPDE, we have to look at a scale in between. So this is already depicted here. So we somehow zoom in, not quite to the microscopic scale, which would look around just 1 point, but to this mesoscopic scale, which is still much smaller than somehow the big scale here. And so this is this magnifying glass here. If we zoom in, then we see these oscillations. And if you want to prove then something mathematically in this program, well, what you would do is to find a microscopic model and then scale out to get a sort of large numbers. This would be this PDE, for example, in the case where things are flat here. And then study fluctuations. So move in again. So look again around this PDE, magnify what's happening here, and then we see some of these oscillations. And yeah, so mathematically, somehow in stochastics 1 terms, this here exactly would be the law of large numbers. And this here would be the central limit theorem around this law of large numbers. And well, if on your microscopic model you have some randomness or some random-like effects. So typically in the models we study, we put some randomness by hand because this makes the analysis easier. You could also imagine that you have a deterministic model, but there's some mixing properties, some chaoticity that is somehow creating randomness by itself. And if this is done in such a way that on the microscopic scale, you have short range correlations, so points which are very far apart on the microscopic scale are nearly independent, then it makes sense to expect that on the mesoscopic scale, which is still somehow infinitely separated from the microscopic scale, you would see space-time wide noise. Why? Well, first of all, these 2 points now, any 2 points which are separated on the mesoscopic scale are actually on the microscopic scale infinitely far apart. And so if you have short range correlations, they will become independent, right? So since they're infinitely far apart, you will not see any more dependence between them. And on the other hand, I mean, if you have some independence properties in there and you create these effects by some superposition, then by a sort of central limit theorem, you would expect to see something Gaussian. So you would expect to see something Gaussian, which is independent as soon as you look in 2 different points. And these points can be in space, but also in space-time. So this would be a space-time wide noise. This is exactly the Gaussian noise, which is independent in different space-time points. And then the variance at the same point, so this is formal notation here, but if I plug in Sx equals Ty, then we would get somehow formally infinity on the right-hand side, right? So we could expect to see SPDEs with space-time wide noise just somehow from this heuristic picture. And indeed, this works and has been extremely well developed since the 80s at least. And there's a strong theory to derive linear SPDEs for fluctuations. So for example, in this interface problem, if we talk about phase coexistence, so where we don't have this systematic motion upwards, but rather we have something fluctuating back and forth, then we would get such an equation. where this here is space-time white noise, this is Laplacian. And now this here is a one-dimensional model, right? For each fixed time, we have a function of one parameter, but you can do similar things also in higher dimensions. So this one-dimensional curve would separate two-dimensional interfaces. And if we talk about three-dimensional interfaces as three-dimensional phases, then the interfaces would be two-dimensional. So, and this here works in principle for any dimension. And there are nice monographs on that by Herbert Spohn and Kipnis-Landin, where this kind of theory is developed. And there's nothing, I mean, there's nothing ill-posed, no? So this works mathematically very well. Now, if you're very careful about how you go about it, then you can also see nonlinear SPDEs in the scaling limit. So it's not super canonical to get them, and just the scaling out typically doesn't work. So typically you will not see a nonlinear SPDE just by scaling out. Instead, you have to prepare your microscopic model very carefully, and you have to tune the model as you scale out in order to see a nonlinearity. So in the interface problem, it's easy to describe. So if you have phase coexistence, so time forward and backward somehow is exchangeable and you're oscillating up and down, then you see this linear equation. If there is a direction of time, and somehow, I mean, direction of time meaning you really move upwards over time, then you would expect to see something else, which is the KPZ fixed point, for which we actually don't really have an SPDE description. And so growth gives you KPZ fixed point, coexistence gives you linear SPDE. And now if you tune very carefully your nonlinearity, then which means your asymmetry, so which means you look at slow growth. So you decrease the speed of this upwards motion in your microscopic model as you scale out. If you scale out more, you make it go slower and so on, but there's always a net motion. Then you will see the KPZ equation, which is the same equation as before, except that we have this quadratic nonlinearity. And now here's this general problem with nonlinear SPDEs with white noise. The solution is non-smooth. I mean, you have the white noise here, which is very irregular. You have some smoothing effect of the Laplacian, which gives you a little bit, but it's not enough. So the solution is still non-smooth. And that's why this quadratic nonlinearity is not well defined, because the psi is too irregular. And so this is what we would call a singular SPDE. It's just one example of a singular SPDE. Now we can solve these equations with progress that we made over the past 10 years or so, going back to work by Heider in 2010, where he noticed that, well, I will comment on that later, where this is coming from. Let's first now try to understand which sort of nonlinear singular SPDEs we can solve nonetheless. And I will simplify this discussion a little bit by looking at equations of this type. So we have some operator A here, we have some noise here. I don't want to specify what they are, and we have some nonlinearity here. You could think of more general things, right? So you could think of quasi-linear terms here, or something which multiplies the noise here, multiplicative noise or so, but just to get the idea across. And actually all the equations we will study will be of this form. So let's just talk about this kind of problem. So this equation is locally subcritical if you can find some parameters, scaling parameters alpha and beta. We require that the beta is positive. Alpha can be anything, such that if you rescale your solution as follows. So what do we do here? We think of lambda going to 0. So we zoom into small spatial scales. Right? If lambda becomes smaller and smaller, that means we zoom into the small scales. And this is why beta should be positive here. We also look at short times. So we slow down time here. And then after that, we make up for it by multiplying with a scaling factor. And this can be with a negative or positive exponent. This is not important. What sign the alpha has could also be alpha equal to 0 if you want. Such that if you do this scaling operation, then this rescaled guy solves basically the same equation, except that, well, here the noise changes on a trajectory level. Is not the same noise at all, but the noise is so that it's law, the noise, so this eta lambda noise has the same law as the previous noise. So on the level of the law, the noise didn't really change. And we have this factor in front of the nonlinearity. And here it's now important that the delta is positive, strictly positive. So this means that if we send lambda to 0, this nonlinearity drops out and we end up with a linear equation. So it means that we could try to understand our solution as a perturbation of the linear equation. And just comment, so delta equal to 0. So that means this factor is gone. So the whole thing is scaling invariant. This is what we would call critical. And delta negative, so this means you blow up the nonlinearity as you zoom into the small scales. This would be supercritical. Yeah, and so since this work, Rough Stochastic PDEs by Martin from 2010, we have found pathwise tools for studying such locally subcritical equations. So in this first paper, it was based on rough paths, and now the most popular tool for studying this is regularity structures. There's also paracontrol distributions, which we developed, and the renormalization group approach. So what I present here is not too connected with paracontrol distributions. If you want to learn about paracontrol distributions, I actually just taught a lecture series about that at FU Berlin. So on my website, and I recorded everything on video because of this online semester. So on my website, you can find the video lectures for a course on paracontrol distributions. But this is somehow a 12-week course or so with 12 lectures. So, and also with much more technical details than I will present here. So what is the basic idea of regularity structure? So the most general theory that we have for solving such equations is regularity structures. And it gives by now, based on this series of papers here by Martin together with Ivan Brunet, Lorenzo Zambotti, AJ Chandra, and Ilya Shevirev, a general local existence and uniqueness theory for, in principle, all locally subcritical equations. There are some under some conditions. So I think if you have space-time white noise, then you should be able to treat all locally subcritical equations. If your noise is too bad, fractional noise, then maybe there's some things where it breaks down. But, so like for those of you who know rough paths, fractional Brownian motion with h less than 1/4, somehow there's no good theory for that. And the idea is, in this theory and in all the other theories, paracontrol distributions, renormalization group approach, and so it's some variation of this idea. It's basically always the same theme. So we freeze the realization of the noise, and then we expand the solution to our equation in terms of the noise, in some sense. And so in regularity structures, you see these generalized Taylor expansions. So this here is a bit of a caricature of it, but so basically you can write u of y as u of x. Actually, this could also go into here. And then you have these derivatives. So you sum over certain trees, and then here you have some evaluation of that tree around the base point x. So x is your base point, and you expand somehow around x and look at what happens for y close to x. And then an error term, which is of order x minus y to the gamma. You should think of gamma as being something positive and sufficiently large. So you could, for example, see that u then is somehow C10 or something like that. And the main difference with the usual Taylor expansion, so in the usual Taylor expansion, you would see here y minus x to the k, and then a sum over k, and then here would be the k's derivative. Well, here you see stochastic terms which are built from your noise. And for example, one term that could appear here is the solution to the linear equation, the linearized equation. Because remember, here I told you that you can effectively drop out the nonlinearity if you look at small scales. So you somehow on small scales a perturbation of the linear equation. So you could expect to see the linear equation in your expansion. Yeah, so the point is that with this new notion of regularity, U becomes smooth and you can actually do analysis, and then you can solve the equation, talk about well-posedness and all that. And the program I want to present here is somehow going orthogonally with that, although the philosophy in some points will actually be the same, but we will implement it differently. And so we don't want to freeze the noise. Instead, we want to understand how the probabilistic, the stochastic process is behaving directly, not for fixed trajectories. And to illustrate this, let's talk about SDEs and how you how you study weak solutions of SDEs. So yeah, the only thing I will basically expect you to know once we get to the true mathematics, all of this is still introduction. The only thing which you should know is stochastic analysis on the level of Ito SDEs and the Ito, yeah, so it's the martingale problem for Ito SDEs. Everything beyond that I will introduce. So we have this STE, then you call X a weak solution if it solves this equation for some Brownian motion. So you don't fix the Brownian motion in advance, but typically if you show that something is a weak solution, you actually build the Brownian motion out of the process X. So you can see somehow this as a function of X rather than the other way around. And well, if we're only interested in the law of our process, then this is perfectly reasonable. No? So then we're not a priori given a noise which acts on our equation, but rather we're thinking about the process and how it evolves, and we don't really care how it depends on one given realization of the noise. And well, this formulation is equivalent to the martingale problem formulation, which just says that for all f in C2b, this process here is a martingale, so f of x minus f of x0, and then this integral here over the generator, and the generator is this differential operator. So classically, you know that weak solutions are equivalent to martingale problems. And so, yeah, I already touched upon this. So this is very different from the pathwise point of view, because we only care about the law, and we don't care about the fixed noise at all, because we actually allow you even to change the Brownian motion in this kind of theory. And now,
sorry,
yes.
there's a question in the chat, and also you have a scheduled break now for 5 minutes for questions in case you want.
Yeah, I think I'm, let me see. Okay. No, okay. I was thinking I have a natural break point, but maybe not. Yes, okay. Let me try. I cannot really see the chat. Let me see.
I can read it out for you if you can't see it.
Yeah, I can see the question now. Let me try to digest the question. So it's not generalizing the rough stochastic PDE paper. That's the short answer. So there are no rough paths coming in. It's rather that we see the nonlinearity as an ill-posed operation somehow on the state space of our solution, which is a function space. And then we need to make sense of that operation on that function space. And we can do this by introducing a suitable measure on this function space. So there's one input from this whole rough path-based theory. And this is the philosophy of thinking about the problem, but we will only see this later. But technically, we don't really use anything from that. So we're not generalizing that those works.
Are there any more questions? So I had one very naive one. So you allowed your, or in the kind of motivation, you allowed your operator to be quasi-linear. What are the microscopic models that go to quasi-linear SPD?
No, I didn't allow it to be quasi-linear. I said I want to only look at linear ones. And you could also imagine doing quasi-linear or multiplicative noise, but in this derivation, I didn't want to present that. But I mean, the question makes sense nonetheless, and the answer is I don't know any model that. Okay. I mean, you typically see the PDE limit, right? So there you can see quasi-linear PDEs. So this happens. So the hydrodynamic limit tends to be nonlinear, and it tends to be actually a quasi-linear. So that you, so that you multiply at least, or that you take the Laplacian of some function of your solution, something like this. But then when you go to the SPDE, you linearize this basically, and the quasi-linear part because the SPD you see on the level of the fluctuations. So you take the limit and you subtract your thing from that now, and then basically you see a Taylor expansion more or less of this quasi-linear term, and that's why you then see something semi-linear.
So are there any more questions? Otherwise, I think we can probably carry on. Okay, yeah, if you want to carry on.
But yeah, then let's take the break now, no?
Oh yeah, okay, you want the break. So maybe
yeah, so I thought it would be
in 5 minutes we come back.
So when do we continue, at 5 or?
In 5 minutes. So
okay.
yeah.
Okay.
Hi. So I think Giuseppe asked the question. I don't know if he's still there.
Yes, so the question by Giuseppe, yeah, so the answer is yes. So we can do theta equals 3/4 under a smallness condition. So if the factor in front of the nonlinearity is smaller than some cutoff value, than some maximum beta 0, then there's well-postness. It's yeah, so this is this work by Lukas Grefner, and I checked it in the weekend and I agree that this is true. So he was not working it out for burgers, but for these quasi-geostrophic equations, but the principle is the same. And then there was the question for the SPDE lecture that I taught at Berlin, and this would be the link. And I will try, so there are also lecture notes for that. For some reason, these lecture notes are behind well, not paywall, university login wall. I will try to make them also available on this website. But like I said, so this lecture, which I mentioned or which I linked to here, has not much to do with the lecture I'm giving here. So this is a different aspect. So this is on paracontrol distributions and rough paths, but not on this martingale problem approach. And to answer Martin's question, no, we don't know. We didn't look into this at all if the process is Gaussian. But yeah, it would be will be somehow the interesting next question to understand this. Yes. For some reason, right, my screen share is gone, and I have the button here to resume. But if I click it, nothing happens. So maybe I stop and then I try again. Okay.
Okay, great. So whenever you're ready.
Okay, so remember this, we talked about this martingale problem. We encode this STE in this operator here, and then we just say, well, if this thing is a martingale, then we have a martingale problem solution, and this is actually equivalent in under some technical conditions, mild technical conditions, to being a weak solution. And now we want to do the same thing. So let's talk about this KPZ equation. Let's try to do the same thing here. So h is a function from r plus times tau to r. And this means that for each fixed time, we're a function, actually a continuous function from this torus to r. So the state space would be something like c t r. And now we need to take test functions on this space. And some of the simplest test function you could think of, except maybe point evaluation, but point evaluation is quite singular. So after point evaluation, the simplest function you could think of is just integrating your h against some phi here. And the phi you can take c infinity, for example. So it's a linear function of your h. And now we would like to write down the generator. Well, how do you derive the generator? You apply Ito's formula. No? So this operator here, one slide back, this operator is exactly what you get from Ito's formula. So this drift here gives you this part. And this here is the Ito correction coming from the martingale term. So we do the same thing. We apply Ito's formula here. We get that this is ht of the Laplacian. Well, just integrating this thing by parts to the other side. And then we have the nonlinearity, and then we have a martingale term. And so the generator for this function, so f of h, we now think of, we take the function f, which just integrates h against phi, so just this function here. And then the generator should exactly be the drift here, the generator acting on that function. So it should be this part, which is fine, and then plus this thing here. But now the problem is that the state space of our process, I mean, before I said it was c, t, r. And of course, a continuous function you cannot differentiate. No? So C1 would be great, but you cannot take C1. So C is not good enough. You can do a bit better. So you can actually keep track of regularity. And then you can see that the state space S is, for example, the space of Hilder continuous functions, which are nearly 1/2 Hilder continuous, so like a Brownian motion. Or if you prefer L2 Sobolev spaces, it could also be H 1/2 minus epsilon. In any case, also on this state space, so this is a bit better than just being continuous, but also on this state space, there's no way of making sense of this operation here, right? So this means that the generator is not defined for all H in the state space. And somehow we're stuck right from the beginning. We cannot even write down the generator, let alone then study the martingale problem associated to this generator. But we could have some hope. So maybe it is too greedy to try to make sense of this for all H. Maybe there's some way in which we could make sense of it for almost all H. Of course, this somehow then requires a measure, and so then you have to really say what you mean by almost all, but this is exactly the route that we will take. So we will not make sense of this for all H in the state space because we cannot, there's no way we can do it. And instead we will make sense of it for almost all. And to understand this almost all, we now transform this problem, and now we go from KPZ to Burgers because this gives us a measure to work with. So the KPZ equation was this equation here, and we wanted to construct this operator here for almost all H. And the question is which measure? And this is easier answered if we go to the derivative of H. So if we differentiate this H here and just formally put derivatives everywhere here, then we see that we get Burgers equation because the derivative commutes with the Laplacian. Here, this thing is just then U squared, but we hit it with another derivative, and also the noise is being hit with a derivative. So this is how this equation comes. It's the derivative of the KPZ equation. And so in principle, it nearly gives you the full KPZ equation, except that, so once we have this object, we could in principle integrate in space, or integrate this thing, then we would get the H back, except that we lose the zero Fourier mode because we have this periodic boundary conditions. So we nearly get the full KPZ equation up to somehow a constant shift. And the advantage of looking at this, why did we do this transformation? I mean, it's just somehow a bit unmotivated, but the reason is that this equation now has a stationary distribution. This equation has a stationary measure, but the stationary measure is infinite mass. So like the stationary measure of the Brownian motion is Lebesgue measure, right? So yeah, it is the stationary measure, but you cannot talk about a stationary Brownian motion because Lebesgue measure has infinite mass. This here is a stationary distribution, which is a probability measure, and that is just the law of the white noise. So this allows us then to address this problem of making sense of the generator for almost all H, or almost all U. And
you have a question from Milton?
Yes. Let me try to see the chat. I lost it again. Yes.
Actually, I think that was a comment rather than a question.
Okay, so this is the right. Yeah, so this is still addressing this theta equals to 3/4. So right, so yeah, so this is what I was expecting. So I know this not from that work by Bernardin Gonçalves, but by this work by Dirk Erhardt, Giuseppe Canizaro, and Philipp Schönbauer, where they also prove something like that for 2D anisotropic KPZ, where they are also able to show that the nonlinearity in the limit is giving some contribution. It is not zero, but the question, so this means somehow the nonlinear equation is not equal to the linear equation, but the question is if the nonlinearity is something Gaussian or not, and this remains to be studied. Yeah, so this martingale approach for Burgers equation goes back to Patricia Gonçalves and Milton Hara, actually already from 2010. And then there were later contributions by Massimiliano Gubinelli together with Milton and Massimiliano and myself. And so this is this program of energy solutions, which is a bit different than what we will do here, but very closely related. And the idea in energy solutions is that you take a stochastic process, which has continuous trajectories with values in distributions on the torus. Here you could also put some, I mean, before we saw that the KPZ equation should have regularity 1/2. So now we take a derivative. So you could imagine this also some h minus 1/2 minus epsilon space. But actually it's convenient not to require any regularity here, right? So it makes it easier to check that some process satisfies all these properties. So the more generous you are here, the easier to check it is. You assume that the law of this process is absolutely continuous with respect to the white noise for all t, and some technical conditions, which I will comment on in a bit. And then, well, actually they can show that there exists a natural way of making sense of this, this generator integrated in time. So you take a test function, which is a bit more sophisticated than the one we look at for KPZ. For KPZ, we just looked at a linear test function. Now we take n linear functions, and then we plug them together into a nonlinearity. So this is what's called a cylinder function. And the easiest thing you could think of, so this phi here should be something nice and regular. The easiest thing you could think of is just taking this one and multiplying it with itself. So the square of this one. And actually taking squares of such function is already enough. But anyway, so you take such a cylinder function, and then you can make sense of this integral with a generator here. So this is well defined. And now, once this is well defined, you can define a martingale problem based on this expression, because this is all you see in the martingale problem. And you can prove existence. And well, you can do this by Galerkin approximation. We will do this in some later lecture, but actually in this work by Patricia and Milton, they proved it by constructing this sort of process as a scaling limit of some weakly asymmetric exclusion process. And in this work, then we were able to prove uniqueness for this process, which satisfies all these properties here, by using the Kolov transform. If you don't know what that means, it's not so important. I don't want to go into detail, but there's a certain transformation with which you can formally linearize Berger's equation. And the linearized equation then is well-posed. So you can map this ill-posed equation to a well-posed equation by some transformation. And what we showed is that this whole set of conditions here is strong enough to allow you to carry out this transformation, to map you really to the Kolov solution. Yeah, some comments. First of all, what are these technical conditions? The main aspect is that you need certain energy estimates, so energy condition. And this is why these are called energy solutions. There's another aspect, a certain forward-backward structure, which we will see in lecture 3 or so. Actually, this will also play a role for us, but which I don't want to get into detail now about. And yeah, but this is the, yeah, maybe the main point is this energy estimate here. One important remark is that really you only construct this integral. You don't construct the integrand. Well, it seems a bit bizarre. How can you construct the integral and not the integrand? The point is that in this construction, this integral here, this is formal notation, and the process you construct really is not differentiable in time. It is looking more like a martingale's oscillating like a Brownian motion, basically. It's a bit better than that, but it is definitely not differentiable. And so this means you don't have the generator. In particular, you don't have a domain for the generator. And actually later when we will construct the domain, we will see that such simple functions, such cylinder functions, are not in the domain of this generator. So the domain for this generator really is much more complicated. And the point here is really that you can make sense of such integrals even for functions which are not in the domain by using the probabilistic structure of the problem. And yeah, the last comment is that this Kolov argument is very, very fragile, because as soon as you change anything about this equation, it goes away. I mean, changing parameters is okay. So you can put some factor here, some factor here, some factor here, that's okay. But as soon as you make a fractional Laplacian here, or you make it multi-component, or you go to these Navier-Stokes type problems also, I mean, there's no way that you can do this call-off argument. So it's really quite peculiar to this model. And so this would have been the breakpoint which I wanted to arrive at earlier. So the goal which we want to do in these lectures is actually to identify the domain. We want to look at a more classical martingale problem, which now is based on this domain. At the same time, we want to keep the link to these energy solutions, because the energy solutions are useful and they're a more hands-on description. Our martingale problem will be quite complicated because the domain for this guy will look quite complicated. And we will look into a uniqueness argument without using call-off transformations. Yeah, so this would be a natural point for questions, if there are any questions now. Otherwise, I would dive into more technical aspects and into the real mathematics of this program. Okay, yeah, so then, yeah, we will now develop technical tools. And like I said, I suspect that I will rather be too basic, but at the same time, I don't want to lose anybody. And yeah, so now, for example, for the rest of this lecture, I will present chaos decomposition. So if you know this, maybe there's no need that you follow that. But since we use some arguments from here and there, from many different points, I don't want to assume that people know everything, and rather would present slowly what we use. So first, yeah, we will work under a Gaussian measure, and we will use chaos decompositions under this measure. And so we should justify why this measure appears. Well, first of all, why do we want to fix one measure? Okay, I already said that this generator is not well defined for all points, so we want to make sense of it for almost all points. And of course, there we need a reference measure. Yeah, so another way of seeing it is the generator is an infinite dimensional differential operator. The generator of an SDE is a finite dimensional differential operator, right? And for an SPDE, the state space is already a function space. So now we talk about differential operators on function spaces. And then if you want to do any analysis there, you clearly need to fix a reference measure. If you do analysis in finite dimensions, you also always have a reference measure. But if you work on somehow a flat space, then this reference measure is always a Lebesgue measure, and you don't really think about it. But here, somehow, the choice actually becomes very important, and it's not so clear if there is a canonical choice, because on infinite dimensional spaces, measures tend to be singular, no? So even something as basic as two Brownian motions with two different variances are singular, the measures of them, because the quadratic variation of this one is sigma 1 squared t, this one is sigma 2 squared t, and this is a path property. And if sigma 1 squared is not equal to sigma 2 squared, then we have a path property which gets probability 1 under one measure and probability 0 under the other measure, so the measures are singular. So we need to carefully choose a reference measure which fits our problem. And well, our problem is this Burger's equation, where now for the first time this square root of 2 appears here, which will become important in the analysis. Because if you don't put the square root of 2 here, you will not see white noise, but some white noise with some weird variance. So this is somehow normalizing the variance of our invariant measure. The invariant distribution is space white noise. What does this mean? This is a Gaussian distribution valued random variable, so it's distribution valued, so it means it's indexed by C infinity functions. It is centered Gaussian, this process, and the covariance is just the L2 inner product of phi1 with phi2, if these are the test functions here. And of course, once you have that, you can extend this to L2 test functions, right? Just by a completion argument, because C infinity is dense in L2. And I told you that white noise is invariant for this sort of problem. But actually, if you think about it, I mean, somehow it falls now out of the sky, I'm telling you about it, but if you think about it with a bit of distance, this is actually quite surprising that you have a nonlinear equation for which you have a Gaussian invariant measure. So if you have a linear equation, like a linear SDE, like an Einstein-Uhlenbeck process, well, then maybe you would expect to see a Gaussian invariant measure, because the solution is Gaussian, since it's a linear function of our Gaussian noise. And then, well, if it's Gaussian for all times, it's converging to some stationary measure, then that measure also has to be Gaussian. But a nonlinear equation, which also has a Gaussian invariant measure, is a bit surprising. And for that, I want to motivate this by describing a general idea or general principle in dynamical systems, which tells you that you can build invariant measures from conserved quantities. And I think this is connected to Liouville's theorem in mechanics, but I'm not so sure. In any case, it's a very simple formal argument, and I mean, this here is purely formal. But of course, then in concrete situations, maybe you can make it rigorous. So let's look at a d-dimensional dynamical system. X dot is equal to b of x. Let's assume that the divergence of b is 0. So b is divergence free. This is important. And let's look at an E, so some sort of energy for our system you can think of, which assigns to each state in our state space a number, so an energy. Each state has an energy. And let's assume that this energy is preserved. So this means if we take the derivative, well, by the chain rule, we see the gradient of E and then the inner product of B of xt. And if this is preserved, then this has to be 0. And well, so essentially, if our X can go everywhere in space, if our dynamics are such that this dynamical system can go everywhere in space, essentially this means that this inner product here has to be 0 for every X. And the claim is that then this sort of measure here is formally invariant with respect to these dynamics, no matter what the lambda is. You can put any lambda here. Of course, I mean, depending how the E looks like, for example, it might only have finite mass if the lambda takes certain values, is negative enough or something like that. But I mean, just from formal considerations, this will be for any lambda invariant. And why is that? Well, there's this notion of infinitesimal invariance, which says that you have to check that your candidate invariant measure integrates the generator of your process to 0. So that this integral here is equal to 0 for all test functions in the domain of the generator. So let's plug in the generator. I mean, this is an ODE, so the generator is just a first order differential operator. It's just this thing here. And now we can integrate this derivative by parts. And once it hits this B here, there we see the divergence of B. And once it hits the exponential, and then the gradient of E comes down. And so here the divergence of B, this is 0 by assumption, so this vanishes. And here we see now the inner product between B and nabla E, so this is 0. And so overall the right hand side is 0, and therefore indeed we are infinitesimally invariant, and this measure should be conserved. Okay, and now let's do an infinite dimensional analog of that. Well, Berger's equation conserves the energy. So the energy is just the L2 norm of the solution. Why is that? Well, remember this is Berger's equation. So now we don't put any noise or so, we just really look at the nonlinearity. And then if we formally differentiate this integral here, then, well, chain rule, you get this, you plug in the equation for delta t of u, you apply Leibniz rule here, so you get 2 times u times derivative of u. So 2 becomes the 4 here, the u is paired here to become u squared, and then you have the derivative of u. And now this thing here is 1/3 times the derivative of u cubed. And now we integrate, therefore, a derivative, and again, we're integrating over the torus. And by periodic boundary conditions, the integral over a derivative is 0, because this would be u cubed evaluated in 1 minus u cubed evaluated in 0, but the two are the same, and so therefore this is 0. Therefore, by this story that we had before, we would expect up to this divergence-free condition, which, I mean, you can also work out how this should look like in this infinite dimensional setting, but let me brush over that. Let's just assume that this works out as well. That this sort of measure is invariant. So we have a lambda and then this energy, and this energy is exactly the L2 norm. And what is the reference measure here? So here it was a Lebesgue measure. Lebesgue measure on RD is just the product measure of the one-dimensional Lebesgue measures over all the D coordinates. Now we formally put the same thing here. So the Lebesgue measure on function space is the product measure over all the coordinates of our function. The coordinates of our function are just point evaluation. So this is very formal. And I put a minus here. Here was a plus, but of course this doesn't change anything, except that here now we really only can take positive lambda. Otherwise this measure doesn't really make sense. But if you put a positive lambda, then, and here I'm going again a bit quickly, but somehow if you think about it a bit more carefully, you can convince yourself that this measure really should be up to a prefactor, which depends on lambda, the law of a white noise. Why is that? Well, in finite dimensions, if you have a measure which is e to the some quadratic form and of x and then dx, then this will be a Gaussian measure, right? So that's somehow the definition of a Gaussian measure. And from this quadratic form, you can read off the covariance of your Gaussian measure. And if the quadratic form is purely quadratic, there's no linear part, then it will be centered. And so, I mean, here we have something which is purely quadratic. So it should be a centered Gaussian measure. And from this, you can read off the covariance formally, and you see that the covariance formally should be like a Dirac delta. So this should be like a white noise. So this explains very, very roughly why we could expect to see a Gaussian invariant measure for this nonlinear equation. Similar features appear in many fluid dynamics equations, so in these Euler surface quasi-geostrophic equations. And so you often have quadratic quantities which are preserved, for example, energy, but also entropy is a similar quantity like that. And this leads to Gaussian invariant measures. So actually, in fluid dynamics, you often have Gaussian invariant measures, and this comes from these conservation laws. Okay, and this, what I was telling now, however, is purely formal. So there's no, there's actually no known way of constructing a solution to Berger's equation, which really is invariant with respect to white noise. So this would be very interesting to obtain something like that, but it is not clear how to do it. The problem is that solutions to Berger's equations are not well posed. They become well posed once you add these entropy conditions, but then you do obtain a unique solution, but this unique solution does not leave white noise invariant. And so you have to look in the bigger class of non-unique solutions and try to find some solution which leaves white noise invariant. Of course, if then your solution is a white noise for each time, then the square here is problematic actually. And so it's not even clear how to interpret the, I mean, how even defining a solution is not so easy. And then constructing one, is difficult. However, if we add this Ornstein-Uhlenbeck process with it, then things work. So this stochastic Berger's, where we add now this linear part in, is really stationary under the white noise. And this is a well-defined process. So this is a superposition of this Berger's dynamics with this Ornstein-Uhlenbeck process, with this linear part here. And let's see. So, I mean, this one formally leaves white noise invariant. So now we should check that this one also formally leaves white noise invariant. So this one here. Because then, I mean, this is always on the level of the generator. The generator of this thing with the sum of these terms on the right-hand side will just be the sum of the generators formally. Ah, there's a question. Yeah, Martin's question is, yeah, no, but I think, I'm not sure, I don't think you can show that the KPZ fixed point solves this Berger's equation in any meaningful way, right? So you can show that it's the, yeah, exactly what Milton wrote. So you can show that it's the limit as you take, so the KPZ fixed point is the limit that you get, at least the conjectured limit that you get by putting epsilon here, epsilon 1/2 here, and then sending epsilon to 0. So, okay, you put them here and here. And then you would expect that this process converges to a limit. And I think on the limit, on the level of the one-dimensional margins, this is shown rigorously that it converges to a limit. Even, okay, even if you start non-stationarily. And this limit should be the KPZ fixed point, but we don't really know that this KPZ fixed point solves this equation. At least, yeah, as far as I'm aware. The question, what does it mean to be stationary under white noise rigorously? So yeah, you can just think, so the easiest way just to say would just be saying that for each fixed time, you're a white noise. You could also think about just taking the process shifted. So you start the SPD in a white noise, and then you look at the equation started at time 0. And so this gives you one stochastic process, and then you look at the stochastic process started at time 1. So you let the equation run until time 1, and then you start somehow again. And you only keep track after time 1. And then these two processes are the same in distribution as processes. But easier to say is just that for each fixed time, you're a space-time white noise. Yeah, so now to prove that this thing, I mean, it's still formal at this point, but that this should leave white noise invariant. Let's prove, however, rigorously that this thing leaves white noise invariant. If it doesn't, then there's no hope that this one should. Right? The Einstein-Uhlenbeck process does. And yeah, you can see this formal, well, no, actually, this is a rigorous argument. You can see this easily by Fourier coefficients. So again, this is our torus here. EK are the Fourier monomials. And so this is an orthonormal basis of L2 over the torus. So if we know all the Fourier coefficients, we know the process. And we define just U hat. So U now solves this equation here. We define U hat TK as UT acting on EK. And then we see that we solve this sort of equation here. And I mean, it's a bit subtle because of the complex valuedness of the whole thing. But okay, first of all, yeah, first let me comment, why do we see this equation? Well, here we get the Laplacian, which we integrate by parts, which gives the second derivative of this thing, so which gives us this factor down here. And here we have the derivative, which we integrate by parts, which gives us this factor. And I mean, if you pretend that everything is real valued, that this here is just a Brownian motion. So this will be a complex valued Brownian motion, but let's just say this is a usual one-dimensional Brownian motion. Let's ignore the I here. And let's look at this sort of equation here. This would just be an Einstein-Uhlenbeck process run at speed 2 pi k squared. Yeah, so we have this factor here, and here we have exactly the square root of that. So this just means that we run the process faster with this speed here. So you can forget about this factor, you can forget about this factor. If you want the invariant measure, it will not change, right? If we let the process run faster or slower, the invariant measure will not change. And then we have this equation here, which is just delta T of U is minus U plus square root of 2 times the Brownian motion. And this is a one-dimensional Einstein-Uhlenbeck process for which we know the invariant measure, which is just a standard normal. So the invariant measure for this kind of guy will be a Gaussian standard normal. Sorry, a complex standard normal. And right, since these things here are independent for different cases, because the noise here is space-time wide, we also see that these coefficients are going to be independent under the stationary measure. And therefore, these are the Fourier coefficients of a white noise. And therefore, we see that the invariant measure for this process indeed is a white noise. Yeah, okay, I'm not going to start this now. So the next point is now, I hope we somehow, I made you believe that the white noise should be the invariant measure for this SPDE. And now we will do analysis under this white noise measure. And for that, we really want to define function spaces. And well, easy function spaces are L2 or LP, something like that. But we want to keep track of regularity. And this here only keeps track of integrability. And so the easiest function spaces on just a finite dimensional space on the torus to work with, I mean, the easiest function spaces to define are somehow differentiable functions and so, but actually they're not so easy to work with. So the easiest functions to work with are, in my opinion, these L2 Sobolev spaces. So where you look at the decay of the Fourier coefficients. And This defines a function space. And the question is if we can do something similar on this white noise space. So if we can find a sort of Fourier transform, so whose decay we can keep track of, and that this can describe the regularity of our functions, now functions on infinite dimensional spaces. And this will be possible by going to chaos decompositions. And this, I will not start now because this is a whole new part, and I will rather describe this tomorrow. So let me stop here.
Okay, thanks. So maybe we can all unmute and clap. Are there any questions? So okay, I have one. So you have this formal Liouville argument, and then you have the rigorous argument showing that the OU process has white noises in invariant measure. How do you combine them?
So this is infinitesimal invariance, right? So the generator. So infinitesimal invariance means, let me write something here, that somehow we have to check that the generator of our thing, of our process, acting on some test function, d mu is equal to 0. And then, well, you can think about whether this infinitesimal invariance is actually sufficient to prove real stationarity and so, but anyways, this is the first step. And now this generator is equal to G, this is the Burgers generator, plus L0, which is the generator of the Ornstein-Uhlenbeck process. And we showed for each, well, formally for the G part, but for the L0 part, we showed rigorously that this integral here vanishes. Well, and for the other one, it formally vanishes. So the sum of the two, I mean, just 0 plus 0, 0. This is the argument.
Okay.
I think Milton has a question.
Yeah. So yeah. Do you want to unmute yourself,
Yeah.
Milton?
Yes. Okay. Thank you. So Nicolas, could you show your last slide, please, again? I have a very silly question. So you define these spaces H alpha. I was wondering if what happens if you put instead of f hat k squared, you put a beta there with some beta or some p basically.
Yeah, so these are these Fourier-Lebesgue spaces. So Massimiliano used them a lot in, for example, in this regularization by noise business and so. Sometimes they're useful. I mean, so first of all, you can define it, and this defines the notion of regularity. And the nice part about the L2 spaces is that, I mean, if you now put alpha to be an integer, this H1 really is what you want it to be. So this means one weak derivative, and the weak derivative is an L2, and your function is an L2. So somehow you can go back from Fourier side to the real side easily by Parseval identity. If you put a P here, this is not so clear anymore. So it's not, so you don't get usual Sobolev spaces. You get function spaces which are more difficult to interpret. Yeah, so for example, yeah, so if you know that your Fourier coefficient, so if you put infinity, right, so this would be the easiest. If you know that your Fourier coefficients decay like k to the minus alpha, this does not mean that you have Hölder regularity of C alpha. You can get some Hölder regularity out of it, but you really lose a lot. But there are these, so what's better then, if you want to go away from L2, is to block them together, the frequencies, in these dyadic blocks. So not look at one frequency, but look at somehow essentially the average over all the k's which are of order 2 to the j. And you first take this average, and after that, you take the absolute value, and then you take LP norms. And this then works. And this gives you the usual Sobolev spaces, essentially. Besov spaces.
Okay, thank you.
Okay, so any more questions? If not, then let's all unmute again and give one last round of applause. So Hendrik or Andres, do you want to say anything before we finish?
Yes, just yeah. Let me just say so. Thanks also to all of the 3 speakers of today. As I said earlier, I encourage you to join our Discord server, and perhaps Andres, if you wanted to put you've already put the link in the chat a few times, but if you could just do it one more time, that would be great. Also. We are going to upload, I think we have some more references that the speakers gave us. We're going to put all of that information on the webpage, and together with the videos of today's lectures, as well as the slides. So everything that was written today, we will put there as well. And yeah, so otherwise, I hope to see you all tomorrow. Did I forget something, Andres?
No, sounds good. Yeah, I'll put also the webpage on the Discord for you to see all the.
Yeah, so yes, so except for that, we see each other. We resume tomorrow morning at 10 UK, if I remember correctly.
That's right.
Okay, so then, yeah, very much hope to see all of you there.
Yep.
Okay.
Thanks, everyone. Bye.
Okay, so let's just end this.